And so our project was to optimize the trajectory of a drone in this case. And so what we wanted to do was, given a friendly or giving two drones, one is friendly and one is malicious, we wanted the friendly one to capture the bad or the malicious drone. What we mean by capture is get close. We didn't really go into detail about how exactly the capturing would take place, whether it would be a net or a projectile. We really didn't want to get into that. And so for our purposes, we say it captures it when it gets close enough, and it's within about 0.1 meters. So some examples of this problem are, say you're at an airport or some other restricted airspace. There could be a drone that is malfunctioning, or perhaps even an irresponsible drone pilot that is flying a drone where it should not be. The idea of our project is you could send out a friendly drone that can go and capture the bad or the malicious drone. Now, that's restricted airspace example, but also there's other examples such as perhaps there's a spy drone or a drone that wants to do some harm with some weapons or some other things. We could send up a good drone that can go and capture that drone so that it doesn't do those harmful things. And so generally our approach was to use two while loops. The second is nested within the first. And so the first while loop runs until the physical distance between the drones is less than some tolerance. And so as we start the first loop is we give it a time step and we predict where the malicious drone will be at the end of that time step. And then we go in and we compute our optimal trajectory to that point. And then finally we update the drone's position for the next time step. And within the second step, the computing the optimal trajectory, that's where we run our optimization. And so we run this until the projected distance between the two drones at the end of the trajectory is great or is less than some tolerance. And so what we needed to do in order to ensure that we had a unique solution is that we used what's called a decreasing horizon approach. So what we did is we said, okay, let's give you some time that's not too long, meaning we can still have a unique solution, but it's longer than the last iteration. And so we say, within that amount of time, minimize the distance to the intruder drone, and then return the trajectory so that we can calculate how far we are. And we would do that again. We'd give it a slightly longer time. It would get a little closer, and then we'd see what the distance was, and we'd continue that until that distance was within whatever our tolerance was. And then, as I mentioned before, we would return to the first while loop and update the drone's position using that optimal trajectory along that time step.
And for our model, we decided to stick to two dimensions, two horizontal dimensions, so we're ignoring gravity for simplicity. And we allowed the malicious drone to use an avoidance scheme. The avoidance scheme that it uses is accelerating in the direction away from the friendly drone if the friendly drone is close enough. And that distance was also a tolerance we could vary for our simulations. For modeling the physics, we used a second degree differential equation, but one for each drone. And we used ODE solving methods to solve the equations. And the physics accounted for the thrust from each drone and the drone mass, and also used a quadratic drag estimate. When the friendly drone estimates the malicious drone future location, it uses an estimate that relies on the malicious drone's position, velocity, and estimated acceleration. And then for the optimization, the constraint we set was that the thrust magnitude had to be less than a given maximum for both drones, but we were only optimizing the friendly drone, so that's where that applied.
So the results we got for the two cases we decided to run are shown below. The two cases we had were we had a malfunctioning intruding drone that had some constant thrust. It was just continuing in a straight line. And that would be, say, in the case of, say, airport security, you would want to send your friendly drone to go in and intercept that drone. And that's shown on the left there. The curves shown are the paths each drone took. And on the right, we have the results for a more malicious security threat that might try to avoid our friendly drone before the friendly drone can intercept it. So here we have an animation of the first case, the malfunctioning intruder with a constant thrust. The paths each drone takes over time looks like this. So as you can see, the friendly drone tries to intercept and eventually does intercept the constant thrust drone. But the friendly drone only has position and velocity information, and it estimates the acceleration of the intruding drone. And because that estimate isn't great, it doesn't know exactly where to go to intercept it. So it does have to correct its course a little bit, but it goes, its course doesn't change too much in order to intercept the intruding drone in this case. For the case where the incoming drone, the intruding drone will avoid our friendly drone once the friendly drone reaches some radius, the path looks like this. So as you can see, the intruding drone continues straight until the friendly drone gets too close, and then it tries to avoid capture. And then both paths of the drones have to change, and our friendly drone's optimization has to change in order to intercept it. But the course is not too different in this case before it ultimately intercepts. So the impact of this project, first of all, the applications. This has applications in defense or for intercepting incoming aircraft or missiles using a controlled drone or aircraft. This has applications in airport security, as we mentioned, where airports have to deal with amateur drone pilots flying and violating their airspace all the time. You might want to go and intercept those drones optimally. And this also has applications in video games for developing AIs that are more challenging or more realistic for players to interact with. Some future work that could be done to expand on what we've done here is first the model could be expanded to 3 dimensions. We didn't include the height dimension in this model, but that could be added. Another thing to do would be to add a more advanced predicting capabilities to the friendly drone. As you saw, the friendly drone's path it could be more straight. If it could predict the ultimate position of intercept better, it could theoretically just make a beeline straight to that point. And you could perhaps do that through an advanced algorithm or perhaps use machine learning to expand the friendly drone's capabilities. Another thing to do is perhaps add optimization to the enemy drone model, because the enemy drone, you could assume that the enemy drone might have its own goals and might have its own optimizer in order to achieve its goals. So you could try and design your friendly drone's optimizer around that fact. Another thing to do is to have multiple friendly drones try and intercept an intruder drone. And so you'd have to optimize multiple paths in that case. Anyway, that's all we have. Thanks for watching.